Hello, everybody, and welcome to our second video of the second ice day. For this one, I'm going to start with a flashback. I want to take you back to last semester, and we talked about a reaction of terminal alkynes with this special boron reagent. And what we talked about was that in this mechanism, there is produced a structure called an enol that spontaneously undergoes what we referred to as keto-enol tautomerization to give the final and more stable keto and/or carbonyl product. Now, I told you that this step happened spontaneously, and we didn't draw the mechanism because I promised I was going to talk about it the following semester. Well, it's now that time to talk about it. So what we're going to do is talk about keto-enol tautomerization. And what I'm going to do is I'm going to go through the mechanism of keto-enol equilibration, also known as tautomerization. Let me write that correctly. And it occurs in either acid or base, which is pretty interesting, but it does happen spontaneously. So first, let's talk about acid. Well, you're getting pretty familiar now with what happens when we have acid around a carbonyl. You know that what we're going to do is add a proton, and the place where we're going to add it is always going to be that carbonyl oxygen. That's going to generate the following positively charged intermediate. Well, what's going to happen next is that we're not going to take this hydrogen back off. If we did that, we would just go back in that direction, and it wouldn't be a productive thing to do. So we're going to take the only other kinds of hydrogens that are around, namely the hydrogen that is on a carbon atom. And when we do that, we're going to generate our enol product. Now, as we're going to see down at the bottom here, the enol is not as stable as the keto form, but it is present. And we're going to have to keep track of that for reactions that we're going to do later today. But in the meantime, I want to talk about what happens in base. Oh, need to point out we take a proton away. In base, as you could imagine, we're going to start by taking a proton away. And this is going to be a bit surprising because we're actually going to take it from carbon. What we're going to do is we're actually going to take a hydrogen that's connected to a carbon, which is not something that you generally do, especially with an oxygen as a base, basic atom. But let me explain something. It's not just any hydrogen. It's a special hydrogen. We call them alpha hydrogens. We call the carbon that is attached to a carbonyl an alpha carbon. And we give it these special designations because they have special properties. In particular, a hydrogen that is on an alpha carbon, the alpha hydrogens, have a pKa in the 18 to 20 range. That makes them relatively acidic, very acidic from the point of view of being a hydrogen on carbon. For reference, an alkane carbon hydrogen is probably closer to 50 or 60 in terms of its pKa. 18 to 20 is actually pretty darn acidic. And the reason for that is when we take that hydrogen away, we end up with a negative charge that is distributed on not only the carbon atom, but also an oxygen through resonance contributing structures. Not only that, we create a pi way. So the bottom line is that the resonance stabilized enolate anion is a lot more stable than you might think. So even though we're taking a hydrogen off of a carbon, in other words, the alpha hydrogen, what we generate, that enolate anion, that is a lot more stable than you might have thought. So that explains why those hydrogens are relatively acidic, and this process actually makes sense. Well, what's going to happen next is we're going to add a proton, but we're going to add it to the oxygen atom, because if we added the proton back to the carbon, we would just go back where we came from, and that's not a productive thing to do. So what we're going to do is we are going to add a hydrogen to that oxygen. When we do that, we get back to our enol form. So the bottom line here is whether we are in acid or base, there is going to be a very rapid keto-enol equilibration, a process that we refer to as tautomerization. But I want to make no mistake, it's the keto form that predominates in both cases, whether we're in acid or base. Don't forget, a catalyst like the acid or base here does not change the position of equilibrium. It just gets us there faster. The reason for both aldehydes and ketones that the keto form predominates is because the C double O bond is stronger than a C double C bond. It's double bond C. So in other words, the C double bond C is not as strong as a C double bond O. Given the difference in bond strengths, the keto form is going to predominate. However, why are we talking about this? Why do we care? We care because something really profound happened. As I'm about to show you, we changed the personality of the keto form, which is mostly as an electrophile to other nucleophiles. We changed to an enol, which is a nucleophile. So we've completely flipped the character of this molecule. Let me explain that. So here we have acetaldehyde in the keto form and the same molecule in the enol form. When we look at these, I want you to look at the electrostatic potential surfaces. This carbon atom right there is mostly blue. It's going to act as an electrophile at that carbon, as we've seen. That's where nucleophiles attack. On the other hand, because an enol has this pi bond, and pi bonds are a source for electron dense or electron dense source, that pi bond can act in a nucleophilic way. Another way of saying it, as we look at that carbon atom, we can see that there is a preponderance of red color. In other words, this is electron rich. That carbon can act as a nucleophile. We have changed the personality, one from being an electrophile to a nucleophile. And just to be clear, an enol you would generally consider to be, didn't mean to do that, you would generally consider an enol to be a weak nucleophile. Okay, now let me get back to this species we talked about right here, the enolate anion. And this is a preview of coming attractions. It turns out that enolate anion is really interesting. This contributing structure, although the minor contributor, still makes a major, let me put this correctly, even though it's a minor contributor, it still makes a significant contribution to the resonance hybrid. As a result, there is a lot of red color associated with that carbon. So enolates, as we're going to learn, are very strong nucleophiles. Okay, just to summarize where we've been. I wanted to take you through the process of keto-enol equilibration, also referred to as tautomerization. And the reason this is important is that even though the keto form predominates, the enol form is always around, and it can act as a weak nucleophile, as it's going to in the reaction that we're going to learn in our third video about to come. Okay, I hope this was useful.